Hello, these are our notes on Charles and Gay-Lussac's laws. These are a continuation of the notes we took on Friday on Boyle's law. So these are more laws dealing with gases and how gases behave. So first of all, Charles' law. Now feel free to pause this as you're writing all this down if I get ahead of you or anything like that. Charles' law is based on the work of Jacques Charles. Lived in the late 1700s, early 1800s in France. He was considered a physicist, although he did a lot of chemistry work as well. Interesting thing about him is that he did a lot of stuff with balloons and studying gases, but a lot of his work he did not publish. And in fact, the relationship we're going to study today about Charles' law, he didn't actually publish. A different guy by the name of Gay-Lussac, who we'll get to in a little bit, published his work and then referenced what Jacques Charles had done, and hence gave Charles's contribution the name Charles' law in terms of the studying he did with his gases. But basically he just took a bunch of balloons, I think it was 5 different ones, and he filled them with different types of gas. So he used oxygen, nitrogen, hydrogen, carbon dioxide, and then regular air. So 5 balloons, and he expanded them, and then he did different experiments with temperature and looked to see how the volumes of those balloons changed. And that's how he came up with his idea of Charles' law. He did a lot of work with hydrogen-filled balloons and made some connections there that they would have enough lift then to go through our atmosphere. And so he was part of, actually, he first did the first unmanned hydrogen balloon flight, and then he did the first manned one as well. First he did it with some other scientists. They were, last name was Roberts. I think they were 2 brothers. But then after that, he actually did one himself as well. And they talk about stories how like Benjamin Franklin was there when this happened. It was at a big exhibition type thing in France. That as they were going through the air, people chased them on horseback to see their balloon go. I think the unmanned one was like a 45-minute type flight, but then when the manned flights went, they were like a couple hours. But his actual law was discovered or credited in the work of Gay-Lussac in 1802. So the law itself is a relationship between volume and temperature. So in this case, we're going to keep the pressure and the moles constant, okay? And then the relationship between volume divided by temperature will stay constant as well. So remember, we talked about this on Friday, that moles, again, refers to the amount. So as long as you have the same amount of gas, you have the same overall pressure going on in the gas, your volume divided by your temperature will remain constant. So V divided by T is a constant then. In this case, it is a direct relationship. So that means that if the T decreases, then the volume decreases. And if the temperature increases, then the volume increases. So this formula here, V1 over T1 equals V2 over T2, I would put a nice big star around that and circle that because that's the technical formula for Charles' law. Now again, you're going to be using this formula so much. The quiz that we're going to have in here on Thursday, you won't be given this formula. You'll be expected to know it, so you'll have to kind of keep that straight with the one that we did on Friday. But then also one other big thing to note, big star, underline, your temperatures must be in Kelvin. For obvious reasons. You don't want negative temperatures or divide by a 0 or that type of thing. So all temperatures are going to be in Kelvin for this, this formula. All right, so if we look a little more at this Charles' law, we can do an example here. So we have our sample of gas, 15 degrees C, 1 atmosphere pressure. The volume is 2.58 liters. What volume will it occupy at 38 degrees Celsius, continuing at our 1 atmosphere of pressure? So the pressures remain constant. We don't have to use that information for atmosphere. So we've got to take our 15 degrees C and convert that to Kelvin. So that'll give us 288 Kelvin. We've got our 2.5 liters, so you can see right here, there's our relationship, our V1 and our T1. And then our second part now, what it's going to occupy, our unknown is V2. and then we've got the 38 degrees C converted to Kelvin 311. So lots of ways I can solve for this. I can just divide by 311 on both sides. Sometimes this formula, I think it's easier just to always think cross multiply and divide if you're used to that, because then no matter where your variable is, that makes that part easier. But if we multiply 2.58 times 311, divide by 288, then we get our final value of 2.79 liters. 3 sig figs for our problem there, because of course we're doing some adding, so we're going to go by the place values there, and then our 2.58 liters has 3 sig figs. Then if you look over here, here's a little graph. This graph shows this direct relationship between volume and temperature. So as I increase my temperature, my volume gets larger. A great example is if you have a balloon and you've ever gone outside where it's cold with your balloon, maybe had it in your car or something like that, and you've noticed that the balloon has, in the colder temps, has seemed to deflate a little bit or something like that. You bring it back inside where it's warm, and then you notice that your balloon is nice and full again. So that's Charles' law, that balloon changing its temperatures. So you can look at here, these are all different types of gas, kind of like what Charles did when he filled the different balloons, and then looked at his data there. Again, direct relationship, and that's what this graph shows. All right, we got 2 slides left. So Gay-Lussac's law is our next one then, named after Joseph Gay-Lussac, or Joseph Louis Gay-Lussac. Again, he was French as well, okay? He also did work with hot air balloons, and in fact, he ascended to 5 kilometers in a hot air balloon, which is, I believe, around like 2,300 feet, something like that. So if you think about that, Mount Everest is 2,900 feet. He got pretty high up in the air on his balloon. Also, he discovered the composition of the atmosphere doesn't change. When he was in some of his hot air balloon flights, he would go up and take different measurements and get different samples of the air and look at the composition of it. And so he kind of discovered that as you go through our atmosphere, the composition stays the same, even though you have different pressures and temperatures and that type of thing. He's also known for helping to discover boron. He also did a lot of work with water and kind of came up with the ratio of 2 hydrogens to 1 oxygen. So he did quite a few experiments and is known for those as well. But like the other thing that I mentioned was that he, when he did his work with pressure and temperature, then he credited Jacques Charles with his work on volume and temperature, and that's how we got Charles' law. So the technical Gay-Lussac's law then is pressure versus temperature. It's very similar, okay? In this case, if I have constant volume in moles, so again, amount of gas that I have is constant as well as its volume, then the pressure divided by the temperature is constant. Another direct relationship. If pressure decreases, then temp will, and if pressure increases, then the temp will as well. So very similar type formula here. Tomorrow in here, we're going to put these all together in what's called the combined gas law. So it'll help make it easier for you to remember all these when we take our quiz in here on Thursday. Again, your temperatures must be in Kelvin. We don't want to be dividing by any zeros. We don't want to be using negative numbers or anything like that. So we're going to keep it in Kelvin to avoid any of those issues. So now your notes are all taken for today. You've got homework that you can be working on. Also, don't forget, if you're interested in doing the retake, you also have that homework to be working on. Use your time wisely. Get this homework done. Tomorrow when you come to class, bring any questions that you have. I'll be happy to answer those. And then we've got a few more notes then on the combined gas law as well. So have a great rest of your day and keep working till the end of the hour. I would like a good report tomorrow. Thank you.